Today we're going to look at exponential growth, but also exponential decay. So for the warm-up, the population of pandas in captivity, or zoos, across the world can be represented by this function, y equals 18 times 1.024 to the x, where x stands for the number of years since 2000. Explain what the following numbers mean, 18 and 1.024, and then about how many pandas live in captivity today. So the 18 is the starting value. So in 2000, there were 18 pandas in captivity. So in 2000, there were 18 pandas in captivity. The 1.024 means that they were growing at a rate of, if I move the decimal over, 2.4% per year. So they're growing at 2.4%. The population is growing at 2.4% per year. About how many pandas live in captivity today? Well, it's 2017, so that's 17 years. So we'll have y equals 18 times 1.024 to the power of 17, and we'll type that in our calculator. 18 parentheses 1.024 to the power of 17. So there's about 20, almost 27, so you can say 26 or 27 pandas. I'll put 27 if I round up. Pandas in captivity today. Okay, so today we're going to look at exponential growth versus exponential decay. So in class, I'm going to have you graph each of the following and sketch them below. So the first is 1.5, 1 times 1.5 to the x. So to do that, we can either use the scratchpad graph or open a graph page and type in 1 parentheses 1.5 to the power of x. We'll graph that. We can see it starts really low by 0, goes through 1, and then it increases. So let's draw that. Okay, how about this? 1 times 2.1 to the x. So I'm going to hit tab to go up and edit the equation that I had. So let's delete this guy and put 2.1. And we can see that's a little bit steeper. Okay, still goes through 1 though. Alright. Okay, so it goes through 1 because that's our starting value, but then the 2.1 makes it steeper. All right, let's take a look at the next two and graph those. So again, I'll hit tab and go up and just edit the ones that I have. So the first one's 1 times 0.25. And this one, again, goes through 1, but it starts up and it goes down. So it looks something like this. And the next one, 1 times 0.6, so again, tab, up. And we can see it looks very similar. Something like this. Okay, so take a look at the graphs. Notice any similarities or differences and why they might look the way that they look. So it says right here, equations from the previous page. Write down the equations that represented exponential growth. Well, the two that were growth were the first two, and the two that were decay were the second two. How can you tell if something will be growing or decaying? Well, the only difference was what was in the parentheses. So if you remember, we have y equals a times b to the x. It has to do with the base. If the base is bigger than 1, it's growing. If the base is smaller than 1, it's decaying. So let's write that down for exponential growth and decay. So for both equations, we have y equals a starting value times b to the x. And we can tell its growth if that b value is greater than 1. And we'll say the absolute value of b. If the absolute value of b is less than 1, so for example 0.25 or 0.6, then it's decay. Here's what growth looks like. Here's what decay looks like. So how does that translate to word problems? Well, let's do a few of those, and this will be what you practice today. Let's say you buy a new computer for $2,100 and the computer decreases by 50% annually. I should put decreases in value. What will the computer be worth in 4 years? So we're going to do our starting value, 2,100. When it was going up, well, first of all, we have to change 50% to a decimal. That's 0.5. So you move the decimal over twice or divide by 100. If it was increasing, we did 1 plus that. But if it's decreasing, it's 1 minus that number. And it will be for 4 years. So here's what it looks like. 2,100. 1 minus 0.5 is 0.5. To the 4th power. We can type that in our calculator. 2,100 times 0.5 to the power of 4, and our computer will only be worth $131.25 in 4 years. Let's do another one. You drink a beverage with 120 milligrams of caffeine. So we should underline our important information. Each hour the caffeine in your system decreases 12%. How long until you have 10 milligrams of caffeine in your system? All right, so let's write our equation. We start with 120. We change our 12% to a decimal, so divide by 100 or move the decimal place over twice, but it's decreasing, so 1 minus the 0.12 to the x power. It says how long until you have 10 milligrams of caffeine in your system? So we have 10 equals 120. 1 minus 0.12 is 0.88, I believe, but let's double check. All right, so you have 88% of the hour before in your system, 88% of the caffeine, the hour before in your system. And now this is guess and check. So what we're looking for here is about how many hours will give us an answer close to 10 right here. So let's type this in, 120 parentheses 0.88, and we're going to guess. So I don't know where to start. I'll say let's try 3 hours. We still have 81 milligrams of caffeine, so 3 hours is too little. Let's go bigger. Let's go 10 hours. So I'll go to the power of 10. Still a lot. Let's do 20. Okay, so it's close to 20. I'm going to say how about 20 was too low, so I have to go a little bit higher. Let's go backwards, 19. Okay, so it's between 19 and 20 hours. Is when it will reach 10 milligrams of caffeine. All right, so the main difference between growth and decay is this B value here. If this number is less than 1 minus our percent, 0.88, then it's decay. So try this today, and we'll review more tomorrow.